Hello and welcome to this tutorial of Perfect Groove. Now we are at version 2 and I thought it's time to show you what is new. In this tutorial I will give you an overview of what Perfect Groove does and how it can help you better understand your vinyl cuts or your audio that you might be preparing for vinyl cutting. So first of all, what is Perfect Groove? It is a standalone application that emulates an analog record cutting lathe. If you own an actual cutting lathe, you can use Perfect Groove to preview and analyze your cuts beforehand with different parameters. This can help you save a lot of time on test cuts and finding the ideal cutting parameters. If you don't own a lathe but are interested in the vinyl cutting process in general, Perfect Groove can help you better understand what will happen to your mix or master when it is cut on an actual lathe. And for those new to vinyl, the tutorial also includes some basic information about how your digital music is transformed into an analog groove on the record lathe. So let's start. Of course, everything begins with your music. So if you open Perfect Groove, it looks pretty empty and there's a little prompt over here to drop in some files. In my case, I created some test signals to begin with, which I'll simply drop onto the window. Now, as you can see on the list, a new side A was created containing our tracks. The list now shows the title and the timestamp for each track. You can also see the waveform for each track below here. And if I hit play, the tracks are played back, so no big surprise here. There's also a little gain knob next to each track where you can adjust the track's volume and an effects button. If you click the effects button, you can add some basic filters to the track, but we'll get to that later when we actually need it. If you're working on a real project, you might want to add a B-side or maybe even more sides if your project spans multiple discs. Let's quickly add another side with this button here and drop in some more tracks. I'll use the same as before. One of the secrets of vinyl cutting is to balance playing time with overall audio level. So if you cut louder, the tracks will also need more space on the record and vice versa. You might find yourself moving tracks between sides until you find just the right balance of playing time and gain. In Perfect Groove, you can simply drag and drop tracks between sides, and the blue timestamp over here will give you the total runtime of each side. For our tutorial, I will work with one side for now, since that speeds up processing a bit. So let's return to our original set of tracks and delete the second side. And since we try to simulate a real project, we'll add some more information. If you double click on the record label, I get a dialog asking for some more information. So let's add PG tutorial as a title. Project ID, of course, is number 42. Artist is me. And client will be you, the internet. Now I think we're good to go to cut this on our virtual record. But what exactly is a vinyl cutting lathe? If you've never seen one, here's a picture of a VMS-80, which is one of the last lathe models produced by German company Neumann in the 80s. Here you can see the platter which holds the lacquer disc. And that looks almost like a normal record, but it is actually a metal plate which is coated with a thin film of acetate lacquer. The heavy arm on the right holds and moves the cutter head, which you can see here with the yellow triangle front. If we turn the cutter head upside down, you can see the two drive coils and the tiny cutting stylus there in the middle. You can imagine the whole cutting process like the reverse of playing back a vinyl record. On playback, the groove moves the needle and induces a current into a coil, which then forms the audio signal. And when cutting, the audio signal drives a coil, which moves the stylus, and which then cuts the groove into a lacquer layer. And if you take a peek through the microscope of the lathe, you can see the modulated groove on the disc. The final important piece of a cutting machine is the control panel, where you can set all the parameters for your cut, and this is where we jump back to the Perfect Groove software. If you click on the little control fader button down here, a dialog will pop up with a set of controls identical to what you can find on an analog lathe. And we will walk through all of them now, step by step. Let's start at the very top with the lathe settings group. You can pick a lathe model you want to emulate, and also a pitch computer which is compatible with the selected lathe model. For our tutorial, we'll stick with the VMS80 now, as it has the most controls and is the most advanced lathe in the software. Next is a calibration group, and this is where the digital and the analog world need to be aligned. Everything that later happens on the actual cutting lathe is an analog signal, but clearly, since we're starting with our audio files, we're in the digital domain now. In order to calibrate our virtual lathe, we need to set two parameters. Number one is the input sensitivity. This value tells us what digital level in dB full scale dBFS is equal to an analog studio level of 0 dB. In the default setting, this is set to -6, which means that a digital signal with a peak level of -6 dBFS will show up as 0 dB analog level at the analog input meter of our lathe. The second parameter tells us what 0 dB input level at the lathe will actually cut on the lacquer disc. If your lathe is calibrated according to the DIN standard, 0 dB will cut an 8 cm per second stereo signal. And if you use the NAB standard, 0 dB will cut a 5 cm per second signal. Or we can select custom here to set our own value for our particular lathe calibration. For the tutorial, we'll just leave it at the default setting of -6 and DIN calibration. Next up is some information about the record we want to cut. You can select a 7, 10 or 12-inch size, and if you're really nerdy, you can also tweak the individual diameters, but for our tutorial I suggest we stick to an RIAA or DIN definition of a 12-inch record. Playback speed for a 12-inch record usually is 33 1/3 RPM, so we can leave that at the default too. Before we look at the other parameters below, we'll actually cut our first record so we can see what the individual settings do to our groove. Let me just switch off pitch and depth control automation and increase the land parameter. This will help me illustrate some things a little better. Okay, I closed the dialog and hit the generate groove button over here. And voila, we have cut our first groove. With our 12 minutes of test signals, we have now filled 37% of the record. And since our tracks are very boring test signals, you can already clearly identify them as individual bands on the record illustration over here. The color you see indicates values of a selected analysis parameter of the groove, but we'll get to that in a minute. For now, we just want to play with our groove parameters a little more. If we move our playhead now, the record will spin and the tone arm will move to the exact spot on the record. And if I click on the little microscope button over here, we can have a closer look at our groove. The silent groove looks pretty boring, but it's a good point to actually compare our groove settings with what we see. Let me open the lathe settings dialog again and let's look at our settings. Let's begin with the groove settings. We've set our basic width to 50 micrometer and the land parameter to 100 micrometer. This means that our unmodulated silent groove should be 50 microns wide and each revolution should be 100 microns apart from the last one. In the microscope view, we can activate a little ruler, zoom in a little bit more, and measure the distance of our grooves and the width of our grooves. So the width is actually 50 microns as expected, and the distance between two adjacent grooves is 100 micrometer. We can also see those two measures up here in the detail window, which shows us several values at the current playhead position. Now if we move over to track number 2, we can actually see our modulated groove with a 1 kHz sine tone. If we zoom into the waveform, you can see it's a mono signal, so left and right channel do always exactly the same. And this is also what we see in the groove. The left and right edge move simultaneously. And if we check our groove dimensions again, the width remains at 50 microns. And since our 1 kHz tone perfectly aligns, the distance between two portions of the groove is always 100 micrometer. Now, what happens if we increase gain on that particular track? Let's raise it by 6 dB and reprocess the groove. As you can see, the lateral excursion of the groove increases. So for a mono groove, the groove width remains constant, but the groove just takes up more space on the record. Let's jump to track number 3. Here we only have a signal on the left channel, and you can see that only one edge of the groove is now modulated. The other edge stays straight. Now our groove width is no longer constant, but it becomes wider and narrower with the modulation of the left channel. In track number 4, we have a sinusoid signal which is out of phase, so left and right channel always do exactly the opposite movement. And the same is true for the edges of the groove as well. This signal now creates very, very narrow parts in our groove, and that is something you really want to avoid. To recap, the two groove settings we were looking at earlier, basic width sets the width of our unmodulated groove, and minimum land or land defines how far these grooves are apart. And when we add an audio signal to modulate our groove, a stereo signal will shape the width and change the width of the groove, and the louder we cut, the more land we need to leave between the individual revolutions. And all of this is true, at least when we have the pitch automation switched off, but we'll get to that in a minute. There are some settings left in our dialog, so let's have a look at those. We've covered basic width and land now, and the third parameter in this group is called second width. The second width is an optional larger width for the unmodulated groove. And with the toggle switches in the other sections, you can set where this increased width is used for markers between tracks, for the lead in at the beginning of the record, and for the lead out groove at the end of the record. It makes sense to increase the width of the groove in these special parts, because this is where the user will set down the needle manually, and you want the groove to catch the needle safely. Speaking of markers, those are the visible separations between tracks on the record. They are not necessarily silent, but they give you a visual hint where the next track starts and where you need to put down your needle. During cutting, these markers are created by increasing the pitch, that is the distance between neighboring parts of the groove, for a specific time. Here you can set the time for such a marker, default is 1.2 seconds, and the increased pitch, here it's set to 1.2 millimeters. If we look at the beginning of a track like here, we can see the marker in the groove. It's the gap right before the new track starts. And if we spin the record, you can see the transition of one track to the next. And if we look really close, you can see that the marker is a little wider than the portion of the groove before it, because we have enabled the second width setting. Let's go back to our track number 1, the unmodulated groove. In the old days, the cutter head was set on a lead screw with a fixed motor, and this created a fixed pitch, that is a fixed distance between groove revolutions. And this is identical to what we did now. But if we look at our silent grooves here, those could be way closer to each other without causing any problems. And even our mono signal could be much closer to save space on the disc. So let's see what happens if we just reduce our land to 10 micrometers. Now the silent grooves are much closer to each other, covering less space on the disc. And also our mono signal needs way less space than before. But what about track number 3 and 4? Since the right edge of the groove doesn't move here, the left edge crashes into it. And it's even worse for track number 4, where left and right edge move in opposite directions. What you see here is called an overcut or kissing of the groove, and would probably result in skipping of the needle on playback. That seems for some portions of the signal we want a really small pitch to not waste space, but for others we need a larger pitch to avoid overcuts. And this is where pitch automation and a pitch computer comes into play. For the Neumann VMS80, this logic is included in the VSA80 control unit, and we can switch it on simply with the automation toggle in our settings dialog. The pitch computer now continuously calculates what distance is needed for the next revolution of the groove and adapts the pitch accordingly all the time. And the land parameter now really acts as minimum land, as it defines the minimum distance between grooves that the algorithm will keep. Let's reprocess our groove and look at the result. So now for our track number 3, we don't have any overcuts anymore, And also track number 4 now leaves exactly 15 micrometer distance between grooves. Our mono signal snuggles up nicely to each other, and the silent groove keeps the same 10 micrometer distance between grooves. Sorry, I think I said 15 before. If we look at our overview again, we now see that we only need 42% of the record compared to over 70% before with our fixed pitch setting. You can imagine that pitch automation was a big step forward in the production of records in the 70s. But pitch is not the only thing that's automated by the computer. Also, depth is controlled. Let's have another look at track number 4. Under the microscope, you can see that compared to our first cut, where we had a fixed pitch, our grooves are not only further apart, but they also became wider. If we use our scale again, we can see that at the narrowest portion, it never falls below 45 micrometer. And this is the second part of the automation logic, the automatic depth control. Whenever the computer detects a too narrow passage in the groove, it widens the groove beforehand, so it stays within the limits we've set when the narrow passage is cut. And the limit it's trying to keep is the basic width, and we can use this parameter min depth reduction to allow it to fall below our basic width by the amount we set here. In our case, basic width is set to 50 micrometer, min depth reduction is set to 5, hence our minimum width should be 45 micrometer. This was now a lot of information about the groove and different parameters. Let that sink in for a minute, take a break, and then we move on to the groove analysis part where I explain the funny colors you probably were wondering about all the time now. I have switched back to a cut with a fixed pitch to illustrate another feature in Perfect Groove, the groove analysis. When the virtual groove is processed, it is analyzed for 4 parameters. First is stylus velocity. How fast does the needle or stylus move on playback? Second, minimum groove width. How thin does the groove become due to out-of-phase modulation? Third, maximum groove depth. So on the other hand, how wide does the groove or deep does the groove become due to modulation and depth added by the automatic depth control? And land as a last parameter. Is there enough space between adjacent parts of the groove? The results of the analysis are displayed as a list of warnings and errors here on the right side, and each warning or error region is also added as an overlay to the waveform. In the groove overview and in the microscope view, a false color scheme is used to indicate the parameter values. The hotter the color, the closer the parameter is to the limit. And you can switch between the 4 parameters down here. And at the moment, the first one, stylus velocity, is selected. In the groove overview, we can see the different colors for each track. And with real music, this, of course, would be a much more broken up pattern. But with our very uniform test signals, this is also a very uniform color. But we can see that track number 2 has the hottest color and also has a warning down here that the peak velocity exceeds our threshold. If we take a look under the microscope, we can see that the velocity of the needle increases and decreases as the groove moves from left to right. In the blue spots, the needle moves the slowest, and in the red areas, the needle approaches our threshold velocity. Now, why is this a problem? When the velocity of the needle becomes too high on playback, it might briefly lose tracking, and that would result in an audible distortion. And in the worst case, it would lose tracking completely and skip. Let's zoom out again and look at parameter number 2, minimum groove width. And there we see that we get a warning for track number 4. If we look at that in the microscope view, it becomes clear that the out-of-phase modulation of our sine tone causes the groove to become too narrow. Our warning over here indicates a minimum value of around 14 micrometer, and the standard specifies a minimum value of 25 micrometers as the minimum. For track number 3, it is touching on orange, but it stays within the limits of the standard. For parameter number 3, groove depth, we don't get a warning or an error, and that is because a too deep groove is usually caused by strong out-of-phase bass signals in combination with the automatic depth control, and this is something we don't have in our test signals at the moment. If you look at the last parameter, land, you see a red and a yellow dot, so this indicates that we have both a critical error and at least one warning. So let's look what's wrong here. Track number 3 shows us a warning that the land becomes too small. And if we look under the microscope, we can really see that the grooves approach each other, but they don't overcut. So this is just a warning. It's still fine. It's not really a problem, but this could cause some issues. And in reality, when you do the actual analog cut, since everything is analog and there's a bit more variation, this could actually result in an actual overcut. And for track number 4, this is a clear overcut, so the grooves touch each other. If you use pitch and depth automation, as we usually do in our projects, you wouldn't get any land warnings or errors because our pitch computer takes care of that. Now with the analysis explained, we are ready for a final example with some actual musical content. For the final example, I've randomly selected a couple of tracks which are high-resolution recordings without too much processing and compression. Let's go ahead and just create a groove with the default settings for an LP. Okay, with our 20 minutes runtime, we now fill our site to 85%. That's not too bad, but we really want to get the maximum out of it, so let's raise the overall volume by, let's say, 2 dB. Okay, now we're at 95% and that's pretty great. Let's look at what our analysis has found. I've still selected the land parameter, so that's all good and taken care of by the pitch automation. But if I switch to stylus velocity, we get 91 velocity issues, which is something we should look at in more detail. Maybe we need to drop the level again a bit after all. Here in the overview, we can already spot some red in the first track and some more at the end of the third track. But we'll check the other parameters first. What about groove width? That's 5 warnings and 4 of them are in the first track. Let's have a look under the microscope. If I double click a warning here, the playhead will move to this exact spot and we can activate the microscope view to check them out. And indeed there are 4 spots where our automatic depth control couldn't compensate for the out of phase signal. Now the question is, what causes it? So let's listen. Okay, so there's lots of percussion going on. And if we look at the absolute values of our groove width, this is definitely something, at least this one, 7.8 micrometer, is something we have to do something about. Otherwise, we risk that our needle just gets kicked out of the groove here. One tool that is often used to fix out-of-phase issues for vinyl cutting is something called an elliptic filter. If we open the effects dialog for our track number 1, we can enable an elliptic filter down here. If we look at the curve, it is a very shallow filter which removes the stereo signal below its corner frequency and only leaves in the mono signal. It is both loved and hated by cutting and mastering engineers, but we'll use it here with a pretty aggressive corner frequency of 300 Hz to fix our percussive issues. The software will tell us that we have to reprocess our groove, so we click process and wait for the result. Okay, we've dropped down to only 2 warnings, and in the first track there's only this one remaining, and now we have a minimum value of 20.6 micrometer, which is closer to the standard of 25 than what we had before. If we really want to be safe, we could of course work on this spot in our digital audio workstation, or for now here, I'll drop the level by 1.5 dB and see if this helps us. Well, not quite, it's 24.4 micrometer, but that's fine. Of course, in a real mix or in a real project, dropping one track by 1.5 dB is not really an option. So maybe you want to look at this particular portion in your mastering workflow and work on it there. But for this tutorial, we'll just use what's available in Perfect Groove. So we have one more warning in the last track, and again, we have an out-of-phase signal, but this time, this is not a percussive issue, but something more repetitive. Let's listen what's going on. Okay, it's a piano piece, and it's just that one particular spot where we go below the threshold. But if we look around, we can see that there's a lot going on in the shape of the groove, and it looks like depth control is working pretty heavily here. So let's look at the other end of the spectrum, the maximum depth. And if we switch to that parameter, we see lots of red and lots of warnings in our last track. From the shape of the groove, we can see that this is not only a low frequency issue, but it covers more of the spectrum. In that case, our elliptic filter will not help very much, or we need to use it very aggressively, and I would go back to the mastering workflow and try to reduce overall stereo width for that piece. Or with imperfect groove, our only chance would be to drop the level a bit. So what about maximum depth in the other tracks? There is a lot of red going on in track number 3, and also a bunch of warnings here in track number 4. Let's listen what's going on here. So track number 3 is an organ piece, and that's something we can definitely fix with a very careful elliptic filter. Let's open our FX settings and let's use one very low at 120 Hz and see if this already fixes our problems. Great, that did it for track number 3. But what about track number 4? So this is a string quartet. And as with the piano piece, this is something probably better to be fixed in the mastering or the mix. Finally, let's now have a look at our velocity warnings. By default, Perfect Groove is set to a very conservative and sensitive threshold of 10 centimeters per second. To get a clearer picture of where the really critical spots are, we can raise that temporarily in the analysis dialog behind the little funnel icon over here. Let's set it to 20 centimeters per second, a value we definitely want to check everything that's above that. In the first track, it's our percussion instruments again that are causing trouble. Percussion instruments in high-resolution recordings often contain lots of high-frequency content that will make the needle move faster than it actually can. If we want to use what's available in Perfect Groove, we can set a pretty aggressive high cut at 16 kHz. Or, of course, we can go back to the mastering chain to tame our high frequencies there a bit. So this really didn't get us rid of all the warnings, and we can have a look at one of them to see what's actually happening. So what we see under the microscope is that it's a pretty straight groove, so there's not much lateral movement, but there's these tiny modulations caused by the high frequencies, which cause our analysis to trigger a warning. There's probably little risk that this groove will kick our needle out of the groove, but the too high velocity might cause some audible distortion. To be really safe, a test cut would give us a definite answer if the needle velocity causes audible distortion or not. Next, let's have a look at track number 2. This is a piano piece with a very clear voice. And it seems that it becomes too fast in this particular spot. In piano and voice recordings, distortion becomes audible very, very quickly. So our safest bet here is to drop the level. If we drop it by 3 dB, we are on the safe side. Again, this is something you probably cannot do in a final master, but then you would have to go back to the mastering chain and see what you can do there. That leaves our string quartet in track number 4, where we also exceed our threshold. String instruments have very rich overtone spectrum, so again, it is high frequencies that cause our needle to exceed our velocity limit. Let's have a peek at the microscope and listen what's going on. We could apply a high cut again, but with overtone-rich instruments, this is maybe something we don't want to do. Or we could do an actual test cut of this particular track to see if the distortion is audible and is actually causing issues. Now we've analyzed and found quite some issues here, and remember that we had raised our velocity limit to 20 centimeters per second. So next we could iterate again with a lower limit and look at everything in more detail. But we'll end this tutorial here and I'll let you fiddle with your own masters. Thanks so much for watching this tutorial, and I really hope you can make use of Perfect Groove in your workflow. I'm out and wish you all happy cutting.